Okay, YouTube, in this video we're going to be discussing the factor theorem and how we could use that theorem actually to help factor polynomials of higher degree that are usually impossible to factor otherwise. Okay, so I say that a polynomial, this is the factor theorem here, and say a polynomial f of x has a factor x minus k if and only if f of that k is equal to 0. So basically what I want to say here is this. We could say f of x, first of all, what I'm saying is has a factor x minus k. So basically what I'm telling you is this goes in evenly, essentially. When we say a number is a factor of another number, then it goes into it evenly. So what this means is if I were to do this now and I'd say, well, let's take some f of x and divide it by x minus k, we would have to say this is the case here. We say the remainder would have to be 0. Remainder, we'll say, is 0. So the definition of something that is a factor of another thing in the first place is that when I divide it out, it goes in evenly or it doesn't go in evenly. And furthermore, what we can say is this x minus k times whatever quotient we get up here, if we were to multiply these back together, then we would totally get what we started with. So what we're going to be doing is this. We're going to be looking for things that have remainders of 0 in order to prove that something is a factor. So this remainder theorem right here, I'm just going to list it one more way. We're saying if I were to list the coefficients here, so we say the coefficients of f of x. And out here we're going to write x equals k. Now it's an interesting thing to write there, but we say if we were to drop in these coefficients, this thing down here is the remainder. But again, remember, not only is it the remainder, it is f of that x value right here. So essentially what we're saying is this. When the remainder is 0, then this thing right here, x equals k, would correspond to the factor x minus k. We say x minus k is a factor. Okay. Furthermore, if that's a factor, then the quotient we get left over, the quotient here, this is also going to be a factor. Okay. So we're just going to put this to use and see what this looks like here. But what it basically says is this. I want you to go factor this polynomial expression for me. Given that we already know that x equals negative 3 causes this thing to have a height of 0. So that's what this says right here. If f of k equals 0, that is, if x equals this number right here, then we're going to get a y value of 0. So now recall from this, we say that a number k is a 0 or a root of the function f because f of k equals 0. That is really what this is saying is this. We say an x-intercept is a root because this is an x value that when you plug it in, you get a y value of 0. So when you're talking about a graph, if you're on the x-axis here, we're saying that you have a y value of 0 and some x value. So not only are we looking for remainders of 0 because something will be a factor, but also we say graphically speaking, we're looking for x-intercepts. So again, let's take this f of x here. We say we already know one of the given zeros or the roots. We say x equals negative 3 is a 0. We'll put it this way, or a root or an x-intercept. So here's how we're going to use this information. This factor theorem up top basically says if x minus k is a factor, then k is a 0, and if k is a 0, then x minus k is a factor. So what we're saying is if x equals this thing right here, then we're really saying this is like our x equals k, and k and negative 3 are the same person. But what this really means is the factor that we're dividing out is also x minus what we usually refer to as k. In this case, our k value we're saying is this negative 3 right here. That's what this is saying. So we'd say negative 3, really then our factor becomes this, x plus a positive 3. So the quicker we learn that basically the factor is usually just opposite the 0, then the better. We say if x is negative 3, then x plus 3 is the factor we're dividing out. So what we know is this. If we're already guaranteed that f of negative 3 is at a height of 0, okay, then what this means is we can put that negative 3 out here and we can drop in the coefficients to this thing right here, 2, 11, 18, and 9. And what we can say is, well, then I guarantee you that this has to come out to be a 0 back here. Furthermore, it means a few other things. So let's go ahead and pursue this. We say negative 3 times 2 is negative 6, plus 11 is 5, times negative 3 is negative 15, plus 18 is 3, and negative 3 times 3 is negative 9, plus a positive 9 is 0. So we say that the remainder equals 0. Remainder equals 0. We also say that this is f of negative 3. And so in other words, if we were to make a table of values for this graph here, we would say that when we plugged in -3, we were at a height of 0 on our graph. So this is also an x-intercept, is what this represents right here. Right there is what I meant to say. And then furthermore, this thing right here, the factor that we divided out, was x plus 3. Okay, and the quotient we left behind is 2x squared plus 5x plus 3. So the rules here were this. It says factor this completely given that we already knew a 0. So what we were basically saying is, yeah, if I know that x equals -3 already works, then x plus 3 is a factor. Oh, and by the way, x plus 3 must go into this evenly, so when I divided it out, I got this quotient right here. And now I could say, well, then my original expression, we're going to write this. We say 2x to the third plus 11x squared plus 18x plus 9 is actually equal to the thing we divided out times the thing we had left over, 2x squared plus 5x plus 3. And as a matter of fact, this thing right here can actually be broken down even further. So we'll just carry this x plus 3 down. We say x plus 3. In this case, we get 2x, I think 2x plus 1 and x plus 3. And actually, that doesn't work there. We say 2x plus 3 and x plus 1. We can check this. We get 2x and 3x give us this 5x right here. So this would be our completely factored expression, and we were able to get all this just by knowing one of the zeros already. So we're going to try this again. It says 1, 0, and actually, sorry, I drew a picture of this function here. We were to say if we were to go find all of its zeros, set this equal to 0 and solve it, then we say if x plus 3 is a factor, then x equals -3 is a 0. And that was one that we already knew to begin with. And if 2x plus 3, if that were to be equal to 0, then we'd get x equals -3 halves. So we would get -3 halves. And if x plus 1 were equal to 0, x plus 1 equals 0, then we would get x equals -1. And I did just make a graph of this a minute ago, but we say, looks like -3 was one of our intercepts. -1 is this other intercept here, -1.303. And we say 2.303. And actually, I typed this in wrongly here. This is a plus, and this is a plus. So I can fix these really quickly here. Actually, I was looking at the wrong function. I was looking at this one right here, and I typed that in actually as this one right here. Okay, so much better. So we have -3, -3 halves, and -1 were our zeros on this one. You can see that those are actually the x-intercepts. So we're going to try this again one more time with this function right here. It says 1, 0 of this function is x equals 2. And so what this really means right here is this. F of 2 equals 0. And it also means that if we were to drop in the coefficients now of this and do some synthetic division, 1, -2, -9, and 18, and then put this x value out here, we say x equals 2, then we are going to find a few things here. We say, well, first of all, 2 times 1 is 2, plus this is 0, times 0 is 0, plus -9 is -9, times 2 is -18, plus +18 is 0. So we have a remainder of 0. We can also say that f of 2 is actually equal to 0. It also means that on our graph, when we plug in an x value of 2, we're at a height of 0, so this means that it is called a 0. This is a 0. And then furthermore, we get this right here. We say x squared plus 0x minus 9 was our quotient with no remainder. And actually what I want to do is I want to point out that this is really x squared minus 9. Furthermore, we said that if x equals 2, this is x equals 2, this is like our x equals k here, then k would have to be equal to 2. So we say x equals k is a factor if and only if x equals k is a 0, if and only if x minus k is the factor. Then what we're saying here is this, then the factor we really divided out here is not x equals +2, but x minus 2 was the factor we just divided out. So what this means is if we were to take this times the answer we got, we would have the original statement back. So in other words, the original statement x cubed minus 2x squared minus 9x plus 18, which I know I had no idea how to factor in the first place, but since I knew one of its zeros in the first place, I was able to use that to find out that really we could rewrite this as x minus 2, which is the thing we divided out, times x squared minus 9, which was the quotient we had left over. And furthermore, this right here is a difference of 2 squares. So we can go ahead and factor it. So we get this x minus 2, x plus 3, x minus 3. So this would mean our zeros are -2, +3, and -3. And we could easily go inspect this on a graph and see that we're actually accurate there. Cheers.